first of all, thank you for inviting me here, and thank you all for staying so long. I hope you will not regret. And today I will bring the 2D materials with gold flakes. And first of all, about the motivation. So motivation came from my boss, Asger Mortensen, and he is a fan of non-local theory. And once he told me, OK, could you please test it somehow? And non-local theory is a special correction to usual theory when you have a strongly confined electric field. And usually you can see it when you have nanoparticles and nanoparticle resonances. It is demonstrated when the resonance becomes broader and when there is a shift of resonance. But there is a lot of uncertainty in nanoparticles. So instead, one can test it with waveguides. And for waveguides, these non-local corrections, they bring more losses and a slight change in k-vector. And we did it in this paper where we studied so-called gap plasmon modes, where you have two pieces of metal, bring them together like a capacitor, and then the plasmons will propagate between these two pieces of metal in a dielectric spacer. So the important part is that first of all, it will be more losses because of non-local response. And then later, if it's even stronger confinement, then you will have change of k-vector. So in order to prove that non-local theory works, and you can show that more losses, you need to remove any other losses. So that's the challenge number one, remove any additional losses. To solve it, we need to use the best material for the structure. So we use the best dielectric, which was atomic layer deposited aluminum. And we used the best gold, which was chemically synthesized gold flakes. And this helps to remove all losses of polaritons, which usually scatters on the roughness. And it also removes all losses of electrons on rough surface and grain boundaries. And the next challenge, which we kind of solved, is we reduced some geometrical uncertainty, which is usually present for nanoparticles. So we don't have any transverse confinement. We didn't cut it into striped waveguides. We used a planar waveguide, so just a flat gold flake. And then it was a well-controlled gap size, because it's atomic layer deposition, which means it's atomic layer precision. Well, actually, later on, we find out that it was not so much controllable gap size, and we decided, OK, the gap will be the free parameter to fit. And then here's the results. We did our near-field measurements. So you can see here the amplitude of the near-field. And, well, it's not a phase. It's a real part of electric field. And you can see the propagation of the modes. And then you can measure both the real and imaginary part of wave vector. When you normalize it, you get effective mode index. So the real part of effective mode index, that's the confinement. And the imaginary part, it corresponds to losses. And then you can see the bottom line is so-called classical when you don't have non-local corrections. And in our case, our measurements show that there are more losses, and we removed any other sources for losses. Therefore, it is a direct proof that there are some non-local corrections. And you can see also a curve from predictions from non-local corrections. Everything lies above. And these non-local corrections, they, as you can see, the most change is in losses. It puts a bit up, and then a small change in confinement. And then it appeared that our measurements are slightly away in confinement. As I mentioned before, we thought we have a good control of our gap. In fact, it's not. Probably it was some air in between or something went wrong there. But this is parametric plot. So we don't use thickness as for plotting it. And therefore, it doesn't matter what is inside the gap. It's still a demonstration that there is some non-local correction should be applied. So that's it. It proves the idea, and everything is done. Everyone is happy. And thank you for the attention. Well, in reality, I was not happy. Because if you look at the electric field, it's not really nice. You can see some waviness in the wavefronts. At that point, we decided to blame atomic layer deposition. So usually it works good, but maybe at this thickness, because usually people they know that it is fine and good material when the thickness is really like tens of nanometers and beyond. But when we go to 2 nanometers, who knows what's going on there. So we decided, OK, let's do the same, but better, and replace this alumina with our 2D materials, with van der Waals crystals. And then with van der Waals crystals, you do with exfoliation, you can go down in thickness as well. The idea was to go down to monolayer thickness. And then these non-local corrections would be even stronger. And then finally, we also realized that we should also check the quality of the gold and contamination. So gold flakes, are they really perfect? If you look in the ACM image, they look really nice. That's ACM, artificially colored, of course. Electron microscope does not give you the color on its own, but they look nice, flat, and almost shiny flakes. Well, when we were working on previous project, we found out when we were measuring topography in IFM, we found that it was some wrinkles. So it was not like perfect flat as you expect it to be. Also, if you do ACM imaging and you tune the contrast to see only the top part of the flake, you can see, well, I'm not sure if maybe you can see it here, that there is some wrinkles also, you can see it in the ACM image. And that's not the wrinkles from the gold flake on its own, that's simply the roughness of the substrate. Here it was the polished glass substrate, and it's not atomically flat. It had some variation, and therefore when you put a gold flake, it follows the same topography. So our conclusion here was that the gold is very pliable, it's very soft. And therefore, to make it smooth, and here it was the thickness 200 nanometers. We could, first we couldn't believe that for this thickness it would still be some waviness. And to make it atomically smooth, you should either use a perfect substrate, like silicon or mica, or you can go to and use gold flakes which are thicker. So, OK, when we start to use thick gold flakes, how smooth are they? In 2022, when we were measuring these thick gold flakes, we were happy to see this topography image with roughness around 0.2 nanometers, and we believed that that was the IFM noise level. Nothing can be better. But still, somehow, I decided to send one sample to Adrian, to NeoSpec, and they did measurements here with the same setup, but slightly upgraded. And there, it was really nice to see that there are some dips. You can see some a bit darker brown spots there. And if you take a profile, the depth is around 0.25 nanometers. That's exactly the same size as atomic step for the gold. And then you can see even that bright terraces, which goes a bit one level up. So then we also believe that there are some small grains. We believe that it was some gold atoms, but it's not. So then we decided to try to see the same in our setup, and then usually when we fabricate our gold flakes, we did chemical cleaning. That means rinsing in toluene, acetone, IPA, and deionized water. And then we got this topography, which I call snot encapsulated. Then we found out that one can use plasma cleaner, oxygen plasma cleaner. And after plasma cleaning, we decided to passivate it and rinse it with deionized water and nitrogen blow to dry it. And finally, we could see these atomic terraces of gold. But still, there are some small bright grains there. And then we learned that there is no need to rinse it with water. Actually, you should take it directly from plasma cleaner and put it in IFM. And finally, we got a nice picture where you see atomic steps of gold without any big contaminations. And then if you mask only the top level, the roughness would be only 0.06 nanometers. That is about the IFM noise level in near-spec system. Then one can, it's a little bit random, but sometimes one can get reasonably large terraces without atomic steps. Well, the scale bar is not really huge, but the size is like a couple of microns. And then we also found that once you do the approach of the FM, it leaves some crater afterwards. So the gold is really soft. And the IFM tip was uncoated silicon tip. And then we decided to see how contaminations grows in time. So we took the gold flake from plasma cleaner and started to scan it non-stop, repeating the same scan. So right after plasma cleaning, it was pretty much clean. The next scan, roughly 3 minutes later, it started to demonstrate some small defects, and more defects, and more defects. So and everything is in ambient conditions, of course. Probably you could get a better results in vacuum. It would hold longer, but in ambient, the contaminations grows really fast, within minutes. Therefore, if anyone except me wants to put something on top of gold flakes, it's better to do it in a glove box. This anyone was our collaborator, Jakob from Korea, from KAIST. First, they asked us to provide some gold flakes. We gave them gold flakes. They put HBN on top. And then they did some snow measurements. Something was not fitting well. Then they brought the sample to the electron microscope. They made a cut and see it in a transmission electron microscope. For us, it was really nice to see that gold crystals is really nice and crystalline structure. You can really see individual, almost like individual gold atoms, and the levels of gold. And then it's also layer structure of boron nitride on top. But in between, there is something. We don't know yet what it is. We call here interfacial layer. Well, we don't care what it is. We want to get rid of it. And it's still work in progress. We still want to know how to remove it and get a pure contact between these two materials. But we also wanted to, coming back to our original goal, we want to replace the spacer with van der Waals materials. So we took our sample, glass substrate, and gold flake on top. And then we put germanium grating. It will be used both for mechanical support of the next flakes, which will be on top, but also for optical excitation. And then we put a TMDC flake on top. And at this stage, we didn't close it with another gold flake. So first of all, we wanted to test this configuration, which is so-called dielectric loaded SPP waveguide. And in SEM and optical image, it looks kind of fine and nice. And then we took it to our near field microscope and did measurements. And here and previously, we used our microscope in transmission mode. And unfortunately, I don't have time to explain it in details. I actually don't have watches. But shortly, here in transmission mode, the illumination and collection is decoupled. So actually, you can shine the light in every point of your sample where you like, and you can still collect the scattering from the tip. And from my opinion, it is superior to reflection mode. We still have reflection mode, but we never use it, actually. And I'm sorry for those who have cryosnom, because transmission mode is impossible there at all. So here we have our near field measurements. And as you can see here, it's not a couple of fringes. It's not 10 fringes. It's as many as you want. And it's the wave just propagates. If there is no losses, or almost no losses, it just propagates. And you can really see there is no limit. And because you can measure a long distance, you have a very high accuracy. So with this system, you can also model. It's very simple modeling. So this system, when you have a dielectric layer on top of gold, it supports both transverse electric and transverse magnetic mode. And this TM mode here, it is a plasmonic mode. And then we did our, we compared with theoretical predictions. And here you can see that, OK, for TE mode it's kind of OK, but for TM mode it's really far from theoretical predictions. And then we were kind of wondering why it happens. So we take a look at the paper, which gives you the parameters for TMDC, and they use ellipsometry to measure, and that's the flakes which they measured, and that was the illumination spot size. So obviously, what was measured is some kind of effective response, average over wrinkles and defects. Another issue with ellipsometry is that you shine light from the air, it refracts, and the refractive index is very large. Therefore, it probes mainly the in-plane component of refractive index. So it's very low sensitivity for the out-of-plane component of refractive index. And therefore, we decided to, OK, maybe we can actually measure the refractive index with snow. So we simplified it even further. We removed the gold flake at all. So we had TMDC, MOS2 on top of glass, again, T and TM modes. And then we compare with theory, and you can see there are also high order of T and TM modes, and you can see there are some mismatches. And Valentin, he might say, of course, for the flakes, you need to use imaging ellipsometry because the size is very small. Well, we also compared with imaging ellipsometry. There is still some mismatch there. And this is raw data. We still need to put the error bars here. We did a similar job with two master students, Tomasz and Stefan, with tungsten disulfide flake, and did exactly the same. And it's only single wavelengths, so it's specifically heterodyne measurements, but with different thickness of flakes. And now you can see the error bars, and you can actually see that the error in effective mode index is very small. And the large error is for the thickness of the flake, which I will tell if the time will be just 2 slides more. But to get rid of the uncertainty in the thickness of flakes, you can also put it in a parametric plot again, because you have several modes supported in the same flake. So you can put effective mode index for TM flake as x-axis, and the effective index for another modes as y-axis. And here you can see that our measurements predicts that it should be something in between these two papers, databases, which is here in these papers. So now about the thickness, just 2 more slides. Hopefully something useful finally for you. So usually you measure the thickness of a flake like following. You do the IFM imaging, then you mask substrate, and you correct linear slope and line shift. And it's almost fine. It's not flat yet. It's kind of bow. Then you do second order polynomial background, and it's almost good, but still not flat at all. So you decide, OK, maybe we should go 1 more polynomial order up, apply third order polynomial background, and everything is failed. So it's not a step anymore. So there is a little bit better approach. What you need to do is first you need to measure a very flat part of the sample with the same scan parameters as you want to use for the step. And here you extract your polynomial background. Then you measure your step. Then you subtract your polynomial background. It's almost good here. And finally, you mask and apply just linear slope correction. And it's nice step size. Finally, OK, the music is on already. So about uncertainty of thickness measurements, when you did the previous steps before, you did all the best for the step. You measure the thickness with 100 nanometers, plus minus 1 nanometer. Let's say error 1%. That's what people usually reported and believe, yeah, fantastic. In fact, it's not the whole story, because you need to calibrate your sample. You take your calibration gradient, and you measure the thickness. It's again 1% more of error. Finally, you look at specifications, and you find out that the thickness is given with 2% precision. Then you need to collect all the errors together, so it ends up with 4%. It could be some different number, but the errors, that's a different story. Yeah, that's it. Oh, no, not yet. So you can also see some IFM artifacts here as overshots. You see it's not completely flat. And actually, I recommend you to read this part. You can Google it in internet. It's very short. It's not even a paper, just a small note about artifacts in IFM. It's good not only for beginners, but also for experts. IFM, those who were here on the first day, you probably remember that IFM is everything except perfectly accurate. So you need to keep it in mind and use your brain when you do the measurements. With that, I would like to thank my colleagues, and I would like to thank organizers, and especially Adrian and Mirko for organizing this event. And if you have any questions, please, thank you.
Thank you very much for this very instructive talk and also showing some of the pitfalls. And I think this is very good to keep that in mind, that when we talk about errors, topography, I think this is really valuable for all of us. So thanks a lot. We might have time for one question. I don't see one. And then maybe, yeah, you have.
Yes. Thank you. Thanks. I guess your gold flake, single crystal flake.
Yeah.
And then the surface would often have reconstruction, herringbone, whatever, which you could see in SDM. Do they play any role in your optical property or not?
Could you please repeat the last
Does
part?
the surface reconstruction of gold surface play any role in the? I mean, you show the roughness can influence some of your measures.
You mean if these atomic steps influence the optical properties?
They are not quite stepped. They even have funny shape. I mean, these reconstruction.
Well, we haven't seen any funny shape. It was like a flat, but there is, of course, it cannot be perfectly flat with one atom level. So it could be terraces, that's what we saw before, but nothing more. So it's the gold flakes have the shape as a flake because this 111 surface, it is more energetically better, you can say. And therefore it's predominantly flat. So when there is one level down, it will be filled up to faster than growing in size. Therefore, it's not so much the surface is not so much different from flat. It can go just one level up and down, but not more. It's not. I haven't seen any funny shape there. Well, it can grow a funny crystal, but you just throw it out. But if it's grown as a gold flake, it's fine. Well, of course, whatever you grow, you go to optical microscopy and see in dark field, bright field, and see that it should look perfect there, first of all.